Push the bottom.
Well, right there.
Hello? Ah, yes, this sounds like everybody else can hear me too. Hi, welcome everyone to the 2023 Bullitt Lecture. I'm absolutely thrilled to have Dr. Jillian Scudder as our speaker, but before we get to that, I would like to invite Mr. Larry Watkins to help me present the Bullitt Prize for Best Paper at the University of Louisville and the Bullitt Scholarship at the University of Louisville to exceptional students. So I'm extremely happy to invite Mr. Larry. Would you be so kind to, we have our certificates here. Let's see, I need Clayton Robinson and Jean-Christophe Gorse up here, please. Sorry, this is part of the thing. You are going to get a certificate, so I'm going to get you out of the audience. Would you like to say a few words? Or?
My grandfather put this collection together over many decades. He had a book dealer in New York City and in London, looking out for the list of first edition books that he wanted to collect. The Newton Principia is the most valuable book, with Newton's own notes, Newton's handwriting on some of the margins in pencil. I've seen the book. And his widow gave the books to the University of Louisville, my grandmother. And then I endowed a book fund to add to the collection, to build it up. And this lecture and award and scholarship and all in memory of grandfather. In fact, he passed away 66 years ago last Tuesday. The next day was Sputnik. He missed Sputnik by one day. But it's a wonderful collection of first edition mathematics and astronomy books. I also have a math scholarship and award in his memory too, and lecture book fund. He actually was a pen pal with Einstein in mathematics. Grandfather went to Princeton. Einstein was a professor at Princeton for a while. And then grandfather, University of Louisville Law School, his portrait is over there in the law school. He became Solicitor General of the United States in the Taft administration. I'd like to think he's the most famous student, alumnus, UL Law School. 1895, Princeton, 1894. In those days, you could go through law school in 9 months. But he was a very, very smart man, very high IQ. So it's a pleasure to do this every year, and that you all could attend, and so enjoy the lecture.
So first off is the scholarship to Jean-Philippe Gorse, I should say. Congratulations. He's graduating this fall, so nice job.
Thank you. Thank you.
And then the Bullitt Prize for Best Paper is to Clayton Robertson. I have a poster for you both here as well from the memory. All right, so thank you all for coming. There was. You were very sneaky. So.
You want more pictures?
Yeah, we always want more pictures. That's fine.
We had the right one.
I think there's 5 cameras that's pointing at us right now. So.
Ready? 1, 2, 3. 1, 2, 3. And third time. 1, 2, 3. 4. One of them should be okay.
All right, so let's I'll get settled. So it is my absolute pleasure to introduce Jillian Scudder. I met her when she was a postdoc at a workshop in Leiden. She was a postdoc at Sussex. I mix up Sussex and Essex. I hope nobody from England is in the room. And Before that, she was a PhD student in Canada at, not McGill. Oh, shoot, okay. Never do this from memory. But she's been a professor at Oberlin for the last 6 years, and that's where I met her again. And I've seen her teach, and it was really fun. So I was like, I should remember and ask. And she's here, and she's written books, and I'm very excited. So hopefully you will be too. I will now give it over to Jill, and hopefully you'll enjoy the lecture. Thank you all.
All right, hello everyone. It is a pleasure to be here, and I'm glad to see that all of you have made it, and I hope you enjoy what is to come, which is described in many times as slight nonsense. We have a title that is Lasers and Styrofoam and Diamond Rain and Other Improbable Stories, and so we will indeed go through lasers and diamonds and rain and styrofoam and other improbable stories. I believe the poster said you should be prepared for raising the stellar dead, toxic clouds of gas, and lasers and styrofoam, and I am a woman of my word. We will do all of these things. So I must first tell you that all of these stories are taken from my book. I am contractually obliged to tell you that I have one and that the delightful people from Carmichael's are outside. So if you enjoy my flavor of nonsense, there is more. Approximately 200 pages more. So let us get oriented. So this is a roughly true color set of images of the planets in our solar system, plus the sun, to size scale and approximately the right colors for what the planets would look like if you were to go observe them with your human eyeball and not have an extremely fancy telescope camera to help you out. The distances, as noted, are outrageously not to scale because I can't fit that on my laptop. So of all of the planets, we have the sun starting out, and we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. We live here. It is the only nice one. All of the other ones are horrendous for various and sundry reasons why. But since we started the talk title with lasers and styrofoam, we should start at the end and look at Neptune. So Neptune is the most distant major planet in our solar system, and this is probably one of the more famous images that we have of it. It was visited by Voyager 2 in 1989 for the first time, and also for the last time. We have not actually sent a single other craft to Neptune since 1989, which means that this image is probably older than a good number of you, which is upsetting to planetary scientists and me personally on a whole number of fronts, in part because I am older than this image. We recognize Neptune by its blue color. This particular image, while it is one of the more famous ones, the color is actually a slight exaggeration. The Voyager 2 camera was designed to be very sensitive to very blue light, and so this is how it was seen by the camera. But if you were to see it with the human eye, it would actually look more like this. Not quite as intense a blue. But it's still definitely blue, and bluer than Uranus in any case. And we know now that the blue color comes from methane, which is a molecule that exists in abundance in Neptune's atmosphere, and which happens to also absorb red light, which means that the light that is reflected is the non-red light, or the blue light. And so we are left with this relatively blue ball. We can see some other interesting things happen. It's not uniformly blue, so there's some regions that must be more methane dense than others. We can also see there's some white clouds. Those clouds are made of ammonia, which is a chemical that we might recognize. Don't breathe it. And so we've got some interesting things happening here. And we did learn a lot from Voyager, even though we only went past it the one time in 1989. So Neptune is 17 times the Earth's mass, compressed into a ball that is just a little bit more than 4 times the size. So this is Earth and Neptune to size scale relative to each other. Obviously, they don't live that close to each other. But if you were to pull Earth out and Neptune, this is how they would appear in size. The Earth is mostly made out of rock and metal, and those are relatively dense materials. So if you're going to get 17 times the Earth's mass into 4 times the Earth's size, we're going to have to crush down whatever Neptune is made out of into relatively high density and high temperatures. Neptune is about 80% things that should be ice. And by should be ice, I mean that if you took a lump of it and left it out roughly at the distance from the sun that Neptune is, it would be solid. It's cold out there. If you put water out that far from the sun, it would freeze solid. Similarly, the other 2 pieces here are methane and ammonia. On Earth, those are gases. And if you were to put them out at that distance, they would be solid. So we call these ices, even though on Earth they're not usually an ice, although water can be. And winter is coming, so it will be. But in order to get things that would normally be ice or exist as a gas to be so dense, we're going to have to really compress them down into a really tight little ball. And so that's what's happening in Neptune. Some other things we learned a lot from Voyager are that Neptune has the strongest winds in the solar system. They are over 900 miles an hour. This is generally considered a bad weather day, except it is permanent. So this is just how Neptune operates. It has super high winds. The other interesting thing we learned from Neptune and have verified since is that it's a little bit warmer than we would expect it to be. So if you take an object and you stick it many, many miles from the sun, there's some sunlight that it will still get. And so that sunlight should heat up your planet. And then it's going to reflect some light, and you can figure out how warm should your planet be if it's just absorbing light from the sun and then reflecting some of that light away. And Neptune is just a little bit warmer than that. So that's a puzzle. It does tell us that something interesting is happening inside Neptune. So as our desire to figure out what's going on in Neptune is now peaked, we're going to try and figure out, well, what's going on inside Neptune? The problem with that is that we've actually never stayed there at all. When Voyager went past, it literally went past and took pictures as it went by. And it was moving relatively quickly. Voyager is now the most distant human-made object that has ever departed the solar system. It's outside of our solar system now. It was going at a clip at that point. This is very much like trying to take a picture of a road sign that you thought was funny as you were going past the road sign on the freeway. Difficult, we managed. We didn't spend a lot of time there. Since then, we've taken some other images of Neptune, but we don't have a lot of high-resolution imagery. This is a Hubble image from 2021. Hubble orbits the Earth, so it is approximately here. And this is a JWST image taken last year, which is much more sensitive to heat. And so the glowing bits of Neptune there are warmer pieces of Neptune. And then you can also see the rings of Neptune, which are almost invisible in every other way. So we don't have a lot of really high resolution images. We have a couple, and they're from 1989. And things have changed since 1989. So we have this problem, which is that we would like to understand the depths of Neptune. And we are not present at Neptune. We have no orbiting craft. We have never had an orbiting craft. And yet, we would still like to understand, how does the inside of Neptune work? We're curious. This is the nature of science. We would like to know more things than we currently know. And as astronomers, we would like to know more things about outer space very specifically. So the solution to this is that we're going to have to figure it out from Earth, which is going to be a challenge, among which the challenges are that Neptune is nothing like Earth. It's not made of the same things. We don't have winds like Neptune, thank goodness. We don't have the temperatures and pressures of Neptune, also thank goodness. And if we lived there, we would die because it's made out of methane, which is bad for you. So we're going to have to try and figure out how to do this from Earth. Challenge number 1. Neptune is a densely packed haze of materials that are either uncommon on Earth or really bad for you. With the exception of the water, we'll give that one a pass. So methane can cause suffocation if you breathe it, and it catches on fire explosively. So we have our first 2 occupational safety hazard signs. I promise more of these. So we have our 2 signs here that methane is flammable, and it comes as a pressurized gas, and if you catch that on fire, it will explode. So methane, 0 out of 10, do not recommend being anywhere near. Second thing, ammonia. Ammonia can be used as a household cleaner, and some of you probably have it in your houses, but you have to be really careful with it, and absolutely under no circumstances mix it with other household cleaners. It will universally make something even more terrible for you. But ammonia in and of itself is toxic and corrosive. And for those of you who haven't seen this corrosion sign before, please note the divot that it's making in this person's hand. That is their symbol for please do not allow this to touch your skin. It is corrosive, it will eat through you. So, we're not going to be working with those chemicals because they catch on fire, they explode, they're bad for you in that if you breathe them, you die, and if they touch you, your hand has a hole in it now. So, not any of those things, please. However, we do still have a model of what the interior of Neptune is like. So this is one of our current models. So this is Neptune at the top. Here's our most famous image with extra blue saturated at the start. And then here's a little slice of what we think the inside of Neptune might look like. So at the very, very top, we have an atmosphere that is made mostly of hydrogen and helium. Below that, we have what we call this ice layer. That's our water, ammonia, methane. That's going to be 80% of the planet. Then we have at the very center this core of probably molten rock, something like the core of the Earth. It's going to be rocky materials, silicates, metal, things like that that are a little bit more familiar. But they're going to be all the way in the middle and very, very toasty and very, very compressed. Things to notice in here that I haven't mentioned. Formation and precipitation of diamond. And then my all-time favorite label on any scientific diagram ever is diamond layer. And the premise here is that we're pretty sure that inside Neptune's atmosphere, diamonds are forming and raining down into the depths of Neptune. And if there is indeed a rocky center to Neptune, then that tells us that at some point those diamonds should be accumulating somewhere. Maybe, unless they're just sinking straight into the molten rock layer, which is possible. So if they are piling up, then we might get a diamond layer. So that's an interesting thing to say. We have so far just told you about toxic chemicals and bad things to breathe, and yet somehow we're going to come to the conclusion that Neptune is raining diamonds. And we're going to do that from Earth without ever having been there or been into Neptune's atmosphere at all. How on earth did we do that? This is the challenge. So, step 1, we're going to have to understand the molecule of methane a little bit better. So let's take some time and do that. Methane is a kind of molecule called a hydrocarbon. And a hydrocarbon is just any molecule that is made up of hydrogen and carbon. We are not inventive namers in the sciences. We just said, okay, what have we got? We've got molecules made of hydrogen and carbon. What's that? Too many syllables. What should we call it instead? A hydrocarbon. Okay, done. Work done, we're great. Methane itself is 1 carbon and then 4 hydrogens, and they're attached together like this. You could write it this way. This is the way I'm going to stick to for the rest of the talk, but you could also write it this way to say it's 1 carbon, C, and then 4 hydrogens, so H4. Or you could draw it out in 3 dimensions. It's actually a kind of triangular pyramid. And so then you would have 3 hydrogens at the bottom, and then the carbon, and then your lone hydrogen becoming a mountain on the top. This is 1 hydrocarbon, and it's one of the simpler ones. But they're a bit like Legos, hydrocarbons, because if you take this one, we can make it more complicated. Let's add in another carbon. Okay, so it's the same thing. We're just going to add in another carbon and more hydrogen. All right, cool. We've made ethane. Okay, I've added in an extra carbon. Oh, that's propane. This one's butane. We've got 4 carbons, 10 hydrogens. This one's nonane, which I picked for the only reason that it's the largest one that fit on the slide without changing the size of my carbons and my hydrogens. But you can just keep going. And your hydrocarbons are just, okay, well, let's just keep adding carbons. We'll keep adding hydrogen. The main thing to take away from this is that these are molecules that are composed entirely of carbon and hydrogen. And that methane is not the only one of these. The main thing that all of these have in common is that they're incredibly flammable. If any of you recognize the names in there of protein and butane, we use those for stoves. And their main job in that role is to catch on fire. So if you want your propane stove to work, ideal. Yeah, let's use propane. If, on the other hand, you would like to have a laboratory that is resembling Neptune in any capacity, we need to compress that gas to a high temperature and a high level of, if there is any match nearby, it will catch on fire really, really well. Methane will explosively catch on fire. If you put propane under high pressure and then you light your propane tank on fire, you will have a bad time. So, our goal now is to have Operation Do Not Set the Research Lab on Fire challenge, which is how do we work with things that are going to be like Neptune, but without catching everything on fire, and without having one extremely stressed scientist being like, if anyone lets any electricity off in this room, we are all having a bad time. Now, I don't know about any of you, but in winter, I personally become a human vector of static charge. And there's not a whole lot I can do about it. So I have empirically tested that I can carry up to 4 volts of electricity of static charge on me. This is not good if you are working with extremely flammable materials. So we're going to not use any of those extremely flammable hydrocarbons. So we're going to instead try to use some other material. We are going to have a couple of criteria here. It should still be made out of hydrogen and carbon. We're still going to try and replicate the interior of Neptune in a reasonable fashion here. So we're going, okay, we need hydrogen atoms and carbon atoms, and that's it. That's all I want in my material. I would also like it to not be extremely flammable and or incredibly toxic. I would like this to be a relatively safe experiment for my lab and my research students and whatever else is going on. Ideally, it could be cheap. That would be perfect. Because if anything is precious in a research lab, it's your time and then your money. So we're going to try our best to find something that's non-toxic and cheap. All right. The good news is we've got one. The funnier news is it's styrofoam. Styrofoam is not extremely flammable or incredibly toxic, or we wouldn't use it as packing material. And it is also incredibly cheap, or we would not use it as packing material. And this poor cat is having a great experiment of static electricity, which means that also it doesn't catch on fire super easily. Great. The next thing that we haven't checked on is if it's made of the right things. And it is. So this is a molecule that's a little bit more complicated than the hydrocarbons I've shown you before, but this is styrene. Another name for styrofoam is polystyrene. And so if you take a single styrene and link it up with a whole bunch of other things, you have polystyrene. And then this chain can keep going as long as you like. And at that point, you've made plastic. Congratulations. And critically, the only elements on here are carbon and hydrogen. So technically, this is a hydrocarbon. And that makes our lives a lot easier, because that's what we were looking for. We needed it to be made of hydrogen and carbon. We got hydrogen and carbon. We got nothing else. So we have reached our goal of let's find something that will not explode the research lab, but will still allow us to pretend that we're on Neptune. So we're going to stay with styrofoam. We had our 3 criteria. We met all 3 criteria. Perfect. Everything is going to plan. We just need to make the styrofoam pretend that it is inside Neptune. Now, I don't know how many of you have spotted this particular problem, but styrofoam is not a very dense material. And the inside of Neptune is notoriously very dense. And if notoriously means from 10 minutes ago, that's fine. So we're going to have to find a way to get styrofoam to pretend to be at very high pressure, or ideally be at very high pressure. And so that is going to be our next challenge. We've got a material that we're happy with, it filled the criterion that we need, but now we need to pressurize styrofoam. Unfortunately, this means we can't actually just put it in a crushing vise, although that would be funny. It won't get us to the densities that we need for Neptune. So we will introduce an extremely powerful laser, which is every scientist's favorite toy. This one is not an extremely powerful laser, which is good. And our extremely powerful laser comes with only one warning. You don't have to point at your eyes, unless you would like very, very amateur LASIK eye surgery, which I don't recommend. I'm not a medical doctor, and I can already not recommend that one. And the laser's job is going to be to heat and pressurize our styrofoam. And then that will allow us to replicate the insides of Neptune. So what we are going to do is aim a laser at styrofoam, which will then make a tiny explosion in our styrofoam, and hit presto, we have made temporary Neptune. So our goal is, we have a laser strong enough, so this laser pointer won't do it, but if we have a laser strong enough, it can heat the material that it lands on. And if you heat the material that it lands on enough, you're going to turn a solid material very rapidly into a gas. And that is an explosion. And if you have made your tiny explosion, it's going to try and explode outwards into the material that was not just superheated. And you're going to start crushing the region around it. So we're going to point it at a block of styrofoam. Wherever it hits is going to cause an explosion. And so whatever size cavity we build out, we're going to compress the region around it. And that is going to give us our region of high pressure. So we're making tiny explosions, and then we're going to see what happens, basically. So this is our miniature temporary Neptune. We have, congratulations, mission achieved, we have exploded styrofoam. Why are we doing that? The goal is that if we can increase the heat and the pressure of the styrofoam, then what we can actually do is take this complicated molecule and completely break it apart into a pile of carbon and a pile of hydrogen. And then we can say, okay, well, what does that do? We have a loose piece of a whole bunch of loose carbon, and we have a whole bunch of loose hydrogen. The loose hydrogen is going to just dissipate because that's a gas and it doesn't feel like hanging around. But if you take carbon at high temperature and high pressure, you can form a crystal. And crystallized carbon can be diamond. You can get other forms of crystalled carbon, but at high pressure, you tend to form diamond. So this is a very elaborate experiment to see if I pressurize a hydrocarbon, will it make tiny diamonds? And so the way that we got to there was like, okay, let's take a hydrocarbon, which is styrofoam, we're going to form a really high-powered laser, and we're going to burst shine onto styrofoam. We're going to make tiny explosions happen, and then we're going to see if tiny diamonds fall out of styrofoam. It totally did. So it worked. They found that they got tiny nanodiamonds falling out of styrofoam by shooting a high-powered laser at it. And from that, we said, well, if we can do this for tiny fractions of a second and make tiny diamonds out of styrofoam when we can only maintain that kind of temperature and pressure for the duration of an explosion, which is rapid? What's to stop Neptune from doing this all the time, but with methane? So methane is a less complex molecule. I showed it to you before. It's just one carbon and a whole bunch of hydrogen. But if you broke apart that molecule, you would have loose carbon and loose hydrogen. And if you do this repeatedly over a large amount of methane, which Neptune clearly has plenty of, is blue, and you've got plenty of pressure, it's crunched down into a pretty small region of space, and you've got time, yeah, that should make diamonds forming in the skies of Neptune. So then you have diamond forming in the sky. Diamond is denser than methane. And anytime you have two materials and one is denser than the other, one of them will sink. And sinking, in this case, means falling down. And down, in this case, is towards the center of Neptune. So this is where we get this sense of, okay, well, if we form diamonds in Neptune, they should also rain down towards the center of Neptune. So this gives us our diamond rain. And we learned about it from exploding styrofoam. Diamond rain sounds cool. It's terrible. Because remember, Neptune has the fastest winds in the solar system. The atmosphere is moving at 900 miles an hour or more. So the other thing to remember is that if you have a really high test need to sandpaper or cut something, you use a diamond bit. So this is what we think this is a thing that we use. You have a diamond drill bit, that's for drilling through something that does not want to be drilled through. If you have a diamond grit sandpaper, that's for sandpapering something that does not want to be sandpapered. Which means Neptune is an industrial abrasive to the tune of 900 miles an hour. You are getting sandblasted with rocks that will sandblast their way through pretty much everything. Please, do not go to Neptune. It will kill you. Isn't space fun? We've got all kinds of problems. Remember I said that Earth was the only nice one? This is the scale of Earth is the only nice one. All right, let's do another one. These next two are going to, we'll do a little bit faster, but that's okay. We're gonna, real quick, just be necromancers. It'll be fine. So one of the things that we have said about outer space is that, okay, well, in some cases, you can take a star that's died and undye it temporarily, and so we have this idea that, okay, well, it's really neat. Some black holes can be necromancers because all astronomers are secretly giant nerds. Some of us aren't that secret about it. So what does that mean? Stars are considered alive when they are fusing hydrogen into helium in their cores. And the star itself is then stable because the light and heat that is, or the light that is produced as a result of that fusion and the energy that is produced as a result of that fusion can counterbalance gravity, which would like to smash the whole thing in together. So we have this delicate balance between fusion going out and gravity going in. But to start fusion, you have to get your star up to something like 10 million degrees. It doesn't matter what centigrade or Kelvin you're using at that point. It's a lot of degrees. If you are going to get fusion going, you also need a lot of densely packed fuel. And the fuel for this is going to be hydrogen, which is not in short supply. When a star forms, it is basically 100% hydrogen. So we're not going to have a problem with fuel for a really long time. And in fact, the sun has been doing this process for about 4.5 billion years. And it will keep doing this for another 4 billion years or so. So we're going to be here for a while sun-wise. The challenge is, and the question is, well, what happens when this starts to fail? So we can only keep fusion going as long as we have fuel in the center. And at some point, because all of that fusion is happening in the core, you will run out of hydrogen and convert it all into helium. So what happens then? Well, then you start reaching what we call the end of life of a star. So up here I have my gravity arrows in red and my fusion arrows in white. And so these are counterbalancing each other. But when fusion in the core of the star stops, then this balance is thrown off. And so gravity suddenly can win for a bit. And what happens next kind of depends on the size of the star. But temporarily, gravity winning means that we crush the center of the star down even more. And suddenly, for a brief window of time, you can create more complex elements. So you take that helium that you built up that was previously useless, and now that we've heated it up enough, we can start building carbon and nitrogen and oxygen and other interesting elements. And also temporarily, you get this ring of, oh hey, the outer parts of the star can fuse hydrogen into helium now. So we have two sources of outward pressure. And gravity is still doing the same job because it only cares about how much stuff there is. And so if you keep this going for a bit, it doesn't last very long, but it's long enough that now that we have two sources of outward pressure, we're going to actually completely blow away most of the star. And so we are left with just the core. And the core is what's interesting here. Because for the core, we have two options. One is, well, the core might be stable. It's not massive enough. It can hold its own against gravity. And in that case, it will just stay there, be a former core of a star, and just gradually cool down over a ridiculously long period of time. If there's too much mass there, and the material in the core of the star can't hold up against gravity, we have a catastrophic collapse. For the sun, we get to the fading away path. So we will have the end point of the sun as just what is now the core of the sun will just be exposed. It's going to hang out. It will be really, really hot for many, many billions of years. And that's all it's going to do. So this is known as a white dwarf. And I'm going to use just a white circle to show you a white dwarf, because there's really not a whole lot of other distinguishing features about a white dwarf. It's small and it's white and it's very, very bright and ridiculously toasty. If you are a more massive star and your core is massive enough, then you can't hold up against gravity, and instead you collapse in on yourself and you create a black hole, which is small. And it's just going to hang out. And if there's nothing nearby, it will just be a tiny gravitational problem in the general area. And nothing else will happen, it's just going to hang out. So we have two kinds of stellar dead at this point. Both of these are not fusing anything anymore, so they are officially dead. They are deceased stars. We can call them dead, or if you want to be technical about it, we can call them a stellar remnant. But stellar dead is more fun. And so we have white dwarfs and black holes. That's the two major kinds. So that's boring. Let's raise the dead. And it's not going to be the black hole because we can't do anything about that one. The other thing to know about stars is that they're, unlike the sun, often found in pairs or with a companion or two companions or three companions. So often you wind up with, oh, I have a really massive star and then I have a slightly different massive star next door. And so you can wind up with two stellar remnants next to each other. And so this system, a white dwarf and a black hole, which are orbiting each other, is possible. And a white dwarf and a black hole would have been a sun-like star and a much more massive star earlier in their lifetimes. But now that they've both gone through their end-of-life process and they have, one has catastrophically collapsed on itself, the other one has just faded away, we're now in this situation where we have a white dwarf and a black hole orbiting each other. They will very, 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 very slowly spiral in on each other. Extremely slowly. This is going to be so tedious for so many billions of years that we are going to do a very professional fast forward. So we're going to skip ahead to the very, very end of this situation that can occur. All right, we're zoomed in. I've officially determined that they're zoomed in because I said so. And the black hole is going to do a magic trick and make the white dwarf temporarily be alive again. So our premise here is that if you have any two objects that are close to each other, they're going to feel the gravitational influence of the other one. And we experience this on Earth with the tides, as we have the moon nearby. And so we have tidal force from the moon on the Earth's oceans. And the Earth's oceans are just more easily deformed than rock, so it's the oceans that mostly pull out. But any object could feel this. And so you get a forwards, the part of the object that faces your massive object is pulled more strongly. And the part of the object that's away from whatever else it's facing is pulled less strongly. So effectively, it's stretched out that way. And then the math works out so that the top and bottom wind up feeling kind of squished. And so if you let this go, your object, if possible, will get stretched out. And so your gravitational force will just distort this object and pull it sideways. So if your black hole is massive enough, and the white dwarf, is close enough, then this will keep happening until you compress it enough and stretch it enough that the inside of this white dwarf becomes so hot and so pressurized that you can temporarily fuse carbon and oxygen into more complex elements. At which point, the black hole is officially a necromancer. And the white dwarf is having a really interesting day. So two things happen at this point. One, this explosion has happened in a very, very, very extended object. It used to be round, it used to be symmetric, it's not anymore. So abruptly we have pressure outwards, and there's an easy way out now, and it's not the long way. So if you create a sudden explosion of pressure, that's an explosion, it's going to find the easiest path outwards. And so what's going to happen is you're going to go perpendicular to the stretching direction and just explode. And what this will do is probably break up the white dwarf into a number of pieces, which will no longer be able to continue to do this. I said that. Cool. The rest of the white dwarf is being turned into the least delicious noodle you have ever encountered in your life. The gravitational force does not stop because there was an explosion happening, so that near part of the white dwarf is going to keep getting stretched out. Which means it's also made out of carbon, which is terrible. That's basically a charcoal noodle. I don't recommend it. It will mess with all of your drugs. All right. Don't eat activated carbon, guys. The white dwarf is only able to actually do this for about 10 seconds. It's actually 10 seconds. In human time scale, 10 seconds is how long this can last. After that, the rest of it just spirals on in to the black hole. This is a one-time event, and it will last 10 whole seconds. So whatever doesn't self-destruct in that instant, in that 10 seconds of explosive, hey, we're going to fuse elements again, gets completely shredded into this spiral or elaborate noodle around the black hole. The black hole is very unbothered by this whole process. It is just going to hang out and do its own gravitational thing, and nothing will change. The white dwarf, on the other hand, is extremely bothered by this whole business. So you can only do this once, but technically the black hole did make the white dwarf fuse again, which does take a stellar remnant, the stellar dead, and make it alive again, just only for 10 seconds. And that's good enough to count. That means that this one is necromantic, and this one's very dead again. Rest in many, many pieces. So we will have, technically, a re-dead stellar remnant, which is now no longer even a single object. What's happened to this white dwarf is basically it's been totally destroyed. So we temporarily switched it back on again, and then it self-destructed, the rest of it got shredded, and we have a pile of gas around the black hole that is now a single object that will do some interesting things for half a minute and then go back to just being a large gravitational lump that will not perturb anybody. So that's silly thing number 2. Here's silly thing number 3. And if you remember from the start of the talk, I promised poison gas, so we haven't done that yet. Well, we have. Here's more. My advice to you is do not drink the gas at the center of the Milky Way, which is perhaps no surprise because everything about this talk has been carnage from start to finish, and all of it has had the moral of it is bad for you. Please do not. So let's talk a little bit about which gas cloud and why. So here's the Milky Way. This is Gaia data. It is a histogram of where stars are in the Milky Way as seen from our perspective. So the Milky Way goes across the center. The dark is just dust. That's not to say that there aren't stars behind those regions. In fact, there are more stars behind that region. Dust is just getting in our way and blocking the light from behind. And so very much in the way that dust is annoying in your house, if you would like to see all of the stars of the galaxy, dust is again not your friend. So we're interested in the gas cloud that's very, very close to the center of the galaxy. And so to give you a bit of perspective, I have a short video that is zooming in from roughly this image, but slightly too far, but I think it's fun, so we're going to look at it anyways. So as we go through this, we're going to cascade through different sets of imagery that has been taken of the center of the Milky Way. So we can zoom in on this, and at some point we will start to switch telescopes and be able to see through this particular gas cloud and see the stars that lie behind it. And then we will crispen up again in a second here. There we go. Even more stars. Now this is in the infrared, so infrared light is able to travel through dust a little bit better, but it does give us a view of what's behind all of these dust clouds. And then here we go. One more time, very nice, very crispy, lots of stars. We could not see all of those stars from our original image, but with careful telescope observations, we do have a sense of what the center of our Milky Way looks like. So this zoomed in slightly too far. We're going to zoom back out again, but just to give you a sense of what things were there. So here's another view of the center of the Milky Way. We have 2 wavelengths happening here. In the blue is, I think, X-ray, so very high energy light. This bit that's bright in the very middle, that's where the supermassive black hole that lives at the center of our galaxy is. And then this in red is where there is gas. And so we're particularly interested in this lump over here, which is called B2. Because again, astronomers aren't good at naming things, and so what happened here is we went, there's like 5 gas clouds, what should we call them? A, B1, B2, B3, B4, B5. Okay, cool. And then we never spoke of it again. So we're in this B2 gas cloud. It's quite close to the center of the Milky Way. And it's been studied for a long time. And the reason it's been studied for such a long time is because we're looking for complex molecules. And in particular, we're looking for amino acids. Amino acids are complex molecules that are viewed as kind of building blocks for DNA and other complicated molecules that are involved in life. And so part of the reason we want to know that is because it's a curiosity of whether or not we need to be building amino acids on Earth from absolute scratch, or whether we're able to sort of have some things baked in for us when we start trying to build life on Earth. So if we are starting to try and say, like, hey, how likely is it that there's life on other planets? Part of that challenge is for things like, okay, well, how hard is it to build an amino acid? And if the answer is, yeah, not hard, it's just baked into the gas cloud that you form planets out of, then that kind of gives everything a leg up. So this is why we've been looking. And we have been able to find some interesting molecules in this gas cloud. One of them is ethanol. Ethanol, we may recognize as grain alcohol. It's also used in hand sanitizer and paint solvent, so this is not necessarily a good thing, but it could be. It is used in alcohol. We also have ethyl formate. Now, ethyl formate is a molecule that on Earth is responsible for the smell of rum and the flavor of raspberries. So, this is potentially delicious. Potentially. And this is where the cover art from the book comes from. It is a raspberry-flavored galaxy drink. The problem comes very immediately. That these are not the only two molecules we have found in this gas cloud. So we expect also a whole pile of hydrogen. There's definitely a whole pile of hydrogen there. But hydrogen isn't like bad for us necessarily. There's plenty of it. It's just, you know, hydrogen is hanging out. It's doing its thing. We're interested in the complicated molecules. So, some other things that we have found in this gas cloud. Formic acid. Formic acid causes burns, and also it damages the optic nerve, which will make you blind if you ingest it. It's also the reason that ant stings and bee stings are so unpleasant, is that they have formic acid in them. There's a particular kind of ant called the wood ant that like sprays acid, which is wildly unpleasant, and if you would ever like to give yourself an intense case of the heebie-jeebies, I invite you to go Google it. It's not, I didn't put it in here for reasons, but they're really unpleasant. So formic acid, I mean, it's an acid. It's not the worst thing, but it is corrosive. What else have we found in this gas cloud? Oh, it's formaldehyde. Yeah, that's a toxic flammable gas at room temperature. So we're going slightly Pokemon on this, and we're catching all of the signs. We've also got a new one. It's carcinogenic in that it will give you cancer. So not only is it toxic and corrosive, it's super bad for your insides. It's traditionally used as a preservative. It is occasionally still used as a preservative, but if you've seen any of these like old style museum collections where you've got a jar of like pickling liquid and some hapless creature inside of it, it's usually got formaldehyde. It also suppresses your nervous system functioning, which is another fancy way of saying you die. Your nervous system is just like, no. No, we're not doing that anymore. But let's stop. Other things you can find is methanol. Methanol is exceptionally nasty. On top of being toxic and flammable at room temperature, if it gets into your body, it digests into formic acid and formaldehyde, which we've already covered are bad for you. Methanol is one of these things that every so often there's a contamination scare. I don't know if any of you remember, but like a year ago or so, there was a recall on some hand sanitizer because it was contaminated with methanol. This is why we don't want it near you, and like you shouldn't drink hand sanitizer anyways, but extra don't drink it if it's got methanol in it. So this is just bad for you, scientifically speaking. Also, we found this. N-cyanide. N-cyanide digests into cyanide, and that just kills you. That's just straight up poison. It's right up there in like you got cyanide and arsenic, things that you should just never ingest, like never have any of this. Yeah, so that's in there too. So our galactic cocktail has ethanol, ethyl formate, which so far is good, and then acid, pickling agent, kills you. Don't drink the gas cloud. Yeah, that is a really terrible idea from start to finish. Just don't do it. There's some helpful things. It's unlikely that you would. If you could get to the gas cloud, it's extremely thin. It's much thinner than air, so even if you were to go to all of the work of compressing it down into something drinkable, one, that would take a lot of work, and two, are you a supervillain? What are you doing? So, yeah, strongly don't recommend it, although if someone needs a science fiction villain origin story, here you go. All right, so here's my takeaway for you. Is that space is filled with some very strange things. And some of them we found out through really weird ways. So like, I don't think any of us would have expected that the way to learn about Neptune is by just shooting a laser at styrofoam and waiting to see if diamonds fall out of that. The context between that and, hey, it's Neptune, is not straightforward. And in fact, I knew about diamond rain on Neptune, and I did not know that it was from lasering styrofoam until I sat down to write out how we had figured that out. So that was very entertaining to me. But we are, as humans, very, very curious creatures, and I think our drive to understand the universe has gotten us to understand things that we cannot, and in some cases will not, ever visit. So in the case of Neptune, we certainly can go visit. In the case of why is Mars bad for you? Yeah, we can go visit there. But in terms of getting to the gas cloud in the center of the Milky Way, no, that's not going to happen. It's simply too far. The human body cannot handle that journey. And then at the end of our discussions and our discoveries, we tend to find out that all of these places are terrible vacation locations. They're filled with poison, they're filled with aggressive sandpapering, or they're just straight up compressive in a way that would kill you. So all of these places are just super terrible for the human body. So on that note, I will end with the line that you should enjoy the Earth, because it is the only nice one. Thank you all for your attention. Questions, I think, is the next question.
I'll run around to this.
I can handle all kinds of weird questions, I promise. All right, we got a microphone running, so stay here.
Is Mars a fool's errand? You need a stratosphere to deflect solar winds, to keep the atmosphere from boiling off. You need gravity to hold an atmosphere. Do you think Musk is a fool? Or do you think one can actually terraform Mars into Earth? Was the core of Mars hot enough to be Earth 1 billion years ago and before they lost its atmosphere?
Okay. Yeah, so there's a lot of questions buried in there, but the idea is that Mars once was much more temperate and once did resemble more like the Earth. So we know now that Mars used to have a lot of water. It no longer has that water, in part because it has lost its atmosphere. In part, it lost its atmosphere because the center of Mars has cooled down. It's cooled down faster than the Earth just because it's smaller. And so there's a lot of things happening there. Are we going to make Mars now into another Earth? No. Could humans still visit Mars? Potentially. There are, however, a lot of problems with visiting Mars outside of the fact that if you go there, you're exposed to a lot of ultraviolet radiation. One of the other things that's in here is there's a compound in Mars that is, roughly speaking, rocket fuel in the soil at levels that is really destructive to the human thyroid. And so if that got into your system, you would have major metabolism problems. So there are a lot of problems with going to Mars, and I think some of them are solvable. They're not solvable on the time scale that Elon Musk would like you to believe. And I don't think they're solvable in the ways that he is trying to do it, but I think there are paths for future human exploration of Mars, but it won't look like being on Earth, and I don't think that's possible.
Another question?
There was a hand up here, and then I see you.
Thank you. Hello.
Hello.
Okay, earlier you said that, okay, so the reason why, or at least part of the reason why the diamonds could possibly likely be forming in Neptune's atmosphere
Yes.
is because they're under really high pressure and that's really dense.
Yes.
So if it's dense, does that mean that that section of, and also you said it was like an ice layer, if it's that dense, then is it like a solid? How are the diamonds like falling through it? How is the wind blowing? Is it like what we understand on Earth as wind, or like what if I could touch it, what would it feel like?
Bad. That one I can answer quickly. So I think that the trick with it is that there are several things happening. So the wind is kind of like a wind on Earth, but it would also be kind of like really high-speed liquid in some ways. So it would be like the world's worst riptide. Then even within water, diamonds should sink. So you just have a difference in buoyancy. And so any material that's denser, then that is going to sink. And so probably it would behave more like a liquid, but it is technically a gas. It's just really dense. So there would be a lot of resistance if you tried to move through it.
Cool.
And then the diamond would abrade anything you were trying to move through it.
Yeah.
Yeah.
Okay, two things. One, is the Eye of Neptune an actual thing on the planet, or was that just a coincidence that it just happened to spot some kind of strange cloud formation?
Is it in the image that I showed you?
Yes, I believe.
This one?
Yeah, that.
Yeah, so that's the Great Dark Spot. It is a big storm. It's analogous to Jupiter's Great Red Spot, and it doesn't seem to be as permanent. So we did happen to see it at a particularly good time. Yeah.
Also, would Neptune explode if you caught it on fire?
Not quite in the same way that we would have it explode here. Part of fire and explosiveness on Earth is because there's a large amount of oxygen in the air, and Neptune doesn't really have the same quantities of oxygen. Now, if you took some Neptune atmosphere and you took that and you put it in a lab on Earth, yeah, it would absolutely catch on fire. But you need the oxygen there, and there's not really any around to catch on fire in that same way.
All right, now when you were talking about the two stars, one being the white dwarf and one being the black hole,
Yes.
and the white dwarf being stretched so much, and at the end of it, that you said that the black hole makes the white dwarf create more complex
Yes.
what was it, elements.
Yes.
What happens to those complex elements when they expand? Do they just go off
Well,
in the universe? Or?
Yeah, so there's two options for that. One is that they explode out so violently that they just kind of drift away from this whole system, and yeah, they just go out into the universe. This is probably happening inside a galaxy, so it'll probably drift off, and maybe it'll mix in with some other gas that's hanging around. And then generally speaking, what happens is you build up the amount of other elements you have in the galaxy. And so then when you try to form planets out of that gas later, you have planets that can form like Earth, where they have lots of carbon and oxygen, and then like neon and argon and other things that you build up out of those
They're
things.
already there.
The other option is that it just falls straight into the black hole.
Okay.
So it's on a scale of very helpful to pointless, but fun nonetheless. I see. Thank you for all your questions, by the way.
So if there is diamond rain
Yes.
on Neptune, is there an analog to the water cycle, or once a diamond, always a diamond?
Oh, I think once a diamond, always a diamond. So I think that's why we have this theory that you're gonna build up a diamond layer. Because you can melt, over here. Diamond doesn't really melt that well. It's pretty stable. So you could create larger and larger crystals. But also once you sink, you're going into higher and higher pressure regions. And so probably the only thing that's gonna happen is you're gonna like purify your diamond. I mean, eventually, yeah. It depends on how rapid this process is. And so probably over like 10 billion years or something, it might get used up, or the amount of methane would decrease. But it's going to happen so slowly that it won't happen within any, like our lifetime. Yeah. Yes.
My question was very similarly related. It
Okay.
was that, is Neptune getting bigger because of this?
It's
It is
not
growing
yeah.
this diamond layer.
Oh, that's actually a really good question. So you mean like spatially bigger?
Yes. Is
So
Neptune growing?
the mass of it won't change, but the density, I guess the density could increase. So, but the actual physical size might not change all that much, because the outer layer will become lighter and more made out of hydrogen. So that'll be fluffier and more loosely attached, and the inner region will become denser. And so the whole thing might stay roughly the same size, but that's an excellent question for planetary scientists.
And if all of the methane was used up to to make all the diamonds, would
Yeah.
you then be able to go there and like be there? Because there's no more diamond rain.
Well, so there would be less industrial abrasive, there would still be a lot of wind, and it would still kill you from pressure.
That's nice.
Yeah, very disappointing, but good question.
Hi. So you said the white dwarf will get stretched, so then it will fuse for like 10
Yes.
human seconds.
Yes.
So like, how long would it be in like black hole seconds? Because like it does like
With
stretch
time
very-
dilation.
Yeah.
So this is the actual work that this is based on was a simulation. And so you're looking at 10 seconds as seen externally from the simulation. So the closer you get to a dense object, or the closer you get to a gravitational object, the slower your time appears to run from an external perspective. So it would probably, yeah, so the person experiencing it would also see 10 seconds, but a person further away would see that 10 seconds happening more slowly. It's a complicated question. So it would, depending on where you are, you would probably still experience, oh, that's 10 seconds. But my 10 seconds and someone on like the white dwarf's 10 seconds would not match up, if that makes any sense. All right, cool. All right. What else have you got? This is the fun part about being a professional Q&A person. Is there another one?
I thought there was a question here.
Maybe not. Oh.
Is Venus the almost star that doesn't light?
Jupiter is the almost star that didn't light. So Jupiter is about a tenth the size that you would need. So it is, but yeah, it is made of almost all the right, it was made of all the right things, and it is warm. It is generating heat just from the pressure of collapsing gas down into a small region. But you would need to be substantially bigger than Jupiter in order to actually trigger a star.
Five of the 8 planets are gas.
We got about half of them. Let me go back to that slide. So the inner 4 are rocky, and the outer 4 are gaseous. Yeah. So once you get to Jupiter, the rest of them are all gas giants. And interior of that, we got Mars, Earth, Venus, and Mercury, which all have solid surfaces. Yeah, you're welcome.
Back here.
You
Yes.
mentioned the rings of
Yes.
Neptune. I was wondering why we can't see them as well as Saturn, for example.
They're much less dense. Saturn's rings, so one is a composition thing and one is the density. So Saturn's rings are like almost entirely water ice, and so they're very reflective, and there's a lot of material held in them. Whereas Neptune's rings are a little bit dustier and darker and made up of other things, and they're thin. So they're really hard to spot if you are looking for reflected light because they're dark. Whereas Saturn's rings are basically just as reflective as you can get. So it's the equivalent of hanging a mirror around Saturn. It's really easy to spot those. We actually now think that Saturn's rings are pretty new. They're only like 100,000 years old or something like that, and probably 2 ice moons collided to create them. So we're kind of lucky to be in a time where we can see them and know that they're there. Most of the other, so Jupiter, Neptune, and Uranus all have very thin rings, more like the ones I showed you for Neptune. I think there was another hand. Do you have a question? Okay.
Second row.
Is there another question? I thought I saw here. Yeah, okay, we got the microphone to you.
So is the diamond layer that's hypothetically on Neptune like one big solid diamond encircling the core, or is it just a big pile?
Well, I don't think anybody has any idea, but my guess would be it would be a giant pile. It's possible that it would be kind of a rubble pile of different sizes of diamond, and probably some of them will have crystallized in weird ways. But since they would have all formed as they were falling down, unless there is a good way of fusing diamonds together, which might be possible but I'm not aware of. My guess would be that it would be a kind of rubble pile of diamond down there.
And if it keeps going, will Neptune end up being a rocky planet, or is it?
It will probably hold on to its atmosphere. And so like Saturn and Jupiter are both mostly hydrogen and helium. And so what would probably happen is that Neptune would become less blue, and it would start to resemble the other gas giants, like over a huge amount of time. Yeah.
So back again to the white dwarf,
Yes.
which was stretched into like a carbon noodle, I think is what you put.
That is what I said.
So when it goes into the black hole, does it continue to be elongated into non-existence, or what do you think would happen to that?
So it will fall in very, very slowly, and so yeah, it will continue to be elongated as it falls in. There's actually a really, really fun technical term for this, and so my usage of the word noodle was not misplaced because the technical term is spaghettification, wherein anything becomes a one atom wide noodle. And so yeah, it will just drop in atom by atom.
And is that like everything that falls into a black hole?
If it's falling into a small black hole, yes. If it falls into a really massive, like a supermassive black hole, the style that's at the center of the galaxy, it'll just fall in wholesale. That will happen later after it's no longer visible.
Okay.
Yeah. We're giving you lots of work to do.
Hey, I love this place.
Yeah, I definitely just wanted to meet you run over here. So, you mentioned that stars come in pairs at times.
Often, yes.
So, does our sun have a pair? And when it dies, would it become the black hole or the neutron star?
So our star does not have any companions. It was formed in isolation, and the nearest star to ours is 4 light years away. So we're actually quite isolated as a star. In general, if you're forming out of a large gas cloud, sometimes you can form 2 or 3 stars all at the same time. And so they would all be collectively at the center of the solar system. So we wouldn't have one star, generally speaking. You can have really wide separated things, but in general you'd have usually two stars at the center of your solar system, and then your planets would orbit widely around that. In the case of our particular star, we don't have enough mass to make a black hole or a neutron star, which we didn't talk about. So we will, our sun will become a white dwarf, and will just continuously fade over the next 20 billion years.
So going back to the spaghettification of a single line atoms.
Yes.
So we know it goes into oblivion, but by observing, I guess, what we know as the universe, is mass still conserved? Like, is energy still conserved when observing those?
Yes, as far as we can tell, because what seems to occur is that once the material is passed into the black hole gains that mass. And so you're just transferring the material from what was the white dwarf into what is the black hole. And so the black hole becomes more massive, and then its gravitational influence becomes stronger. So you're conserving mass in that way. We're just no longer able to retrieve any information about what's happening in that area, because the black hole doesn't allow us to know things about what's happening inside of it.
Early on, you mentioned that Neptune seems warmer than we think it should be based on solar energy and
Yes.
how much it reflects. Sorry if I missed this, but do we know why?
It's probably the aggressive sandpapering it's doing. Genuinely, that's one of the theories, is that the diamond rain is functioning as enough of a source of friction that it's able to heat itself up by sandpapering its own insides. Yeah. Isn't it?
My last astronomy class was 1979.
Yes.
So you need 10 to the 33rd power grams of hydrogen to make a little star.
Yes.
And you said fusion would stop at carbon, not iron.
Fusion stops at carbon if you are a low mass star. If you are a high mass star, then the process of catastrophic collapse does create elements up to iron. So that is where those come from. Beyond iron happens also in the process of catastrophic collapse. So you have the supernova, which precedes the formation of a black hole, and then others and eventful things in the universe create heavier elements. But yes, for a star like the sun, fusion will stop at carbon and oxygen. But for more massive stars, you're able to build up, where we had that, you have a core fusing helium.
What is a red giant?
So that is the phase where you have helium at the center. Helium is fusing into carbon, nitrogen, and oxygen at the center. And then you have that ring of hydrogen fusion around that. That is when you get your red giant star. And that's how you lose your outer layers. All right.
All right. Her books are on sale outside.
They are. I will even sign them if you want.
Right. And if you want them signed, we will do that. So thank you. Let's thank the speaker again, and thank you all for your questions. I just have to say thank you as well.